Thank you very much, Dr. Saleh. What a wonderful menu of innovations. There's so much to learn. I wish we have time to study. Don't you feel like it's too much to learn? So many interesting things, difficult to understand and to follow. My talk is different. I'm going to talk about the future and give you some of my thoughts on the past and the present of optics and where it's heading. And I just like to tell you that we've celebrated the 25th anniversary of CREOL, the College of Optics and Photonics, and I gave a similar talk there that attracted some interest, and SPIE has kindly invited me to share this with the larger audience here. So let me just begin with the landmark 1998 NRC report, Harnessing of Light. That report has really captured the importance of optics and photonics and the challenges facing the field at that time, and has coined the word pervasive enabler, optics appearing ubiquitously in every aspect of the technology, and has discussed scientific policies and issues. And in the last decade, it's almost 14 years, a number of applications and new ideas and innovations have appeared, and it was felt that there is need for another report, and there it is. But let me just also point out that another report that focused on the science of atoms, molecules, and photons covered optical sciences from a different perspective. It pointed out 6 compelling research opportunities for optical sciences: ultra-fast lasers and ultra-cold atoms, ultra-cold atomic molecular and optical physics, and some of its applications in coherent quantum gases, high intensity and short wavelength sources, ultra-fast quantum control, quantum engineering, and quantum information. And these were the basics of the report. And with all these reports, what good were they? They were of interest to scientists, but not much interest to others. We particularly care about government and US agencies. The funding agencies in the US in particular have spread their coverage of funds over many departments and many agencies, and has not really so far recognized optics as a discipline of its own. And a good example of that is NSF. You see these directorates, and you don't see the word optics really appear directly. It appears in an implied way, and it is spread across the different agencies. And but of course, optics and photonics production occurs in a limited, only 15% in North America. European Union has followed on harnessing of light and have created their own reports. One such report is the Strategic Research Agenda, which was prepared by Photonics 21. It's a European technology platform representing European industry. And they prepared a report in 2006 and a second that was published in 2010. These reports were more practical. They defined some of the technologies that you see here, as my laser pointer is dead. But they defined key recommendations. I just highlight particularly very concrete recommendations like doubling the funding for photonics. The industry should invest 10% of its turnover in R&D, green photonics as an emphasis, developing, of course, a skilled workforce for photonics. These are concrete, particularly doubling the funding. And I hope that the Harnessing of Light 2, the one that we will all see in a couple of days, has addressed or has pointed out some concrete steps in this direction. Harnessing of Light 2, that's not the name. I think I have a pointer here. Thank you. That's to be released in a couple of days. And I think, as was advertised in the beginning, this report will be presented by some of the authors on Wednesday in the afternoon. So with that said as a background, let me just talk a little bit about the future. I added the word on because this is just thoughts on the future of optics and photonics and not specific predictions. Prediction is very difficult, as we all know. Who could have predicted going in this direction from the vacuum tubes to the transistors to the IC to 1 billion transistors on a chip? Who could have predicted that? Could we have predicted this? Maybe some. That the Mac, the early Mac, would lead to this iPad. Could we have predicted this? Well, when Moore's law was established, people didn't believe it. And then when years passed and it still works, people began to use it to predict. And it works. So there is prediction that can lead to some correct answers if it is linear. This is linear on a log scale in this case. But technology doesn't work this way. There is evolution and there is revolution. If you spot this is the time axis, which is missing. If things follow this path, what would happen? You would make a prediction and then discover that things have saturated and never materialized in the way that's expected. Then you see a disruptive idea that pushes the field forward with a different slope, a couple of them here. You could see progress in a different way where an idea reaches its limit and people give up. Then you have what I call resurrected, frustrated disruptive ideas. Here's another situation where you have ideas that are hyped. So people discover that they were too hyped. And then they lose faith and it goes down and no one is interested, no funding. But then it could be resurrected again. And there are examples of this. I would just like to show you how I saw optics evolve along these patterns that I showed in the previous slide. The old optics, venerable old optics, described perhaps in the first edition of the Principles of Optics, Born and Wolf book. And maybe that's in the 50s, 60s. And then what are the disruptive ideas? The disruptive ideas are 3 disruptive ideas: the lasers, fibers, and semiconductor optics. These are definitely disruptive technologies. It has created this society, this large audience. But was the laser really a disruptive idea? I would say that perhaps the people who invented the laser were really seeking an optical oscillator much the same as the audio oscillator and the radio oscillator and the microwave oscillator and then the masers and then the lasers. They were just pushing things in a linear direction along higher and higher frequency. So there is an innovation that really, it predicts that eventually we'll get a coherent source at optical frequencies, and they were able to do it, but it was a disruptive technology. Of course, lasers begat nonlinear optics and integrated optics and ultra-fast optics about the same time. And ultra-fast optics is now generating the strong interest in high harmonics, in atto-optics, X-ray sources, so extending. Now you're going not just masers and lasers, you're going X-ray lasers. So that's really an extrapolation that defines a goal which might not be realizable in a decade or 2 or 3 or 4. Eventually it gets done. We're talking 5 decades here. And then after that, what comes? Quantum information. Is this really new? Well, quantum mechanics was even before the laser. And the ideas of, and of course, quantum optics began with the lasers in the 60s. When Glauber got the Nobel Prize, that was for his work in 1963 on coherence and quantum theory of light. But then 4 or 5 decades waited until you have a disruptive idea. I would say the disruptive idea in this case is perhaps the idea of using the non-clonability of the quantum states to do quantum key distribution or cryptography. That has resulted in an expansion, an enormous expansion in the field of quantum information. And then, of course, comes nanomaterials, and we've just heard this beautiful expansion description of the expanded field. There we have metamaterials, plasmonics, and photonic crystals, and then more which I don't know. And it's very hard to predict, but one can predict along linear paths, as I will explain to you in a minute. This is an example of resurrected, frustrated, disruptive ideas. Holography. Holography was invented before the laser. Dennis Gabor got the Nobel Prize for his work in the 40s. But holography did not really become a reality until the technology became possible thanks to the invention of the laser. Photonic crystals. Jablanovic has had the idea as a nice theoretical construct. But it took him years of playing with microwaves and millimeter waves before it became optical photonic crystals. Negative index, a similar thing one would say on Veselagu inventing the concept of negative epsilon and negative mu, and that only now bringing the fruits that we have just seen in the previous talk. So this is just a view of how technology and how scientific ideas progress. I'd like to give you a framework for guessing about the future of optics and photonics by defining the applications of light in terms of applications based on the transfer of information and others based on the transport of energy. The transmission of information is limited by the ability to localize. The ability to localize light in time or frequency, the ability to localize light in space or direction, the ability to localize light in energy. By that I mean the precision with which you can select a certain value of amplitude or energy. That's localization. And to do more localization means you advance the technology. I'll explain that more. So it is really localization, localization, localization as a theme. And the next point is the use of light as a carrier of energy, not information, is limited by the efficiency of energy conversion to and from light to anything else. And that has to do with the process of interaction with matter. So there, efficiency, 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 and to do both, you need materials, and there, I think it's very, very important, as we've also learned in the last talk, materials, materials, materials. So let me dwell on these three. If I have time, I'll come to the end of this. So the principal applications of light, I also like to present them in these 4 words: reading, writing, communicating, and computing. By reading, I take the generalized sense. Reading means seeing, means microscopy, means astronomy, means sensing, probing, extraction of stored information from a memory, etc. That's reading. Reading in the general sense. What is writing? Writing is printing, lithography, display, actuation, forces applied on something, manufacturing, cutting, welding, photochemistry, photosynthesis, etc. You can read the rest. And the two together require an improved, in order to progress, there would be need for improved resolution in space. That's resolution spatially and spectrally, resolution in time to be faster, better accuracy with lower power, moving from 3D to 4D to 5D. 5D is X, Y, Z, T, omega. Communicating faster at greater data rates, longer distances or shorter distances, interconnect. Communicating with less error, communicating among more users, communicating more securely, and progress of optics will be along all these dimensions. Computing faster, more flops per second, solving difficult mathematical problems that take even the largest computer to solve, simulating, etc. So the next thing is not just reading and writing, but reading and writing through thick media. By thick media, I mean media that can be absorptive, scattering, diffusive, inhomogeneous, fluctuating, moving, nonlinear media, or moving around objects. So penetrating deeper to read and write. And remember, read and write in the general sense. And to shape and bend beams around objects. How can light travel around a corner, enter the next room, and come back and give me the information I want? Can that happen? Oh, yes, it can. And there are some recent things, the beginning of light bending to go to the next room and read something. And that is going to be, meeting these challenges that I have articulated is going to be the future of optics. So let me now just take you through the axes of time and space and energy. Space first. What are the limits? Are there hard limits on localization in space? Maybe one could say the wavelength. But can we beat the wavelength limit? Oh, yes, we can. Can we beat the wavelength limit by much? This is the challenge. Time. What is the limit in time? Well, the optical cycle. Can we squeeze light to a fraction of an optical cycle? We have come to a few cycles. Can we squeeze light there, and what happens to the spectrum then? What are the challenges when you come to these limits? But time and space, space are not disconnected, they're coupled. Lambda and omega are coupled by C. And so therefore you have to look at the two in their coupled way. And then amplitude or energy, or the polarization of course comes into the vector amplitude. Now what are the bounds there? The bounds are perhaps the photon energy. The photon energy is in the less than A2 joule. And are there bounds in the high energy? There's nothing physical. So if you create a volume along these three-dimensional axes, this is the domain with which we work. And all we do as we progress in optics is expand that domain along the axes of time and space and amplitude. And by amplitude, I mean precision of amplitude. So let me just say a few words about time. The limit, as I said, is optical cycle. And forget this other limit, the Planck time. That's just an esoteric limit. And there, the time limit has to do with the pulse width. Pulse width is very important if you want to send data. But there is more to it, the switching time. The ability to switch a device is not the same as the pulse shape. Next thing is the response time of a device or a communication channel or a detector. What are the limits on these? And of course, how this translates into the spectrum. This graph shows progress in squeezing or reducing the pulse width. You would see here the Moore's law line. You would see here the progress is the same slope. And it hit Now, this is the optical cycle, femtoseconds. And we've gone into attoseconds, or it's 100 attoseconds or so. That is where the field of atto-optics resides. And the prediction is that it will continue to make the pulse shorter and shorter, but we're getting there. You know, we're approaching the limit. And of course, as you become shorter, you occupy a very large spectral width. You cover the entire optical spectrum, and then you'd have to deal with materials and material dispersion. Switching time. You could see here in this list multiple technologies, from semiconductor optical amplifiers to liquid crystals to magneto-optics to electronics, of course, along the scale of time, getting shorter as you go up in the axes. If you go there in the detection and the response time there, the progress is, again, these are APDs dealing with 40 gigabits per second and more. Now, the time spectrum profile, not just getting a pulse, but shaping the pulse. Precision synthesis of the optical electric field is a challenge of today, and is getting better and better. Temporal and spectral characteristics of the waveform, engineering it and designing and producing it the way you want it. And there comes optical frequency combs as a very precise, discrete set of frequencies which you can combine in a precise way to obtain any shape or form, any waveform that you'd like to obtain. And this would result in the future, the expectation is to have chip scale frequency combs spanning an octave as a commonplace technology. Massively parallel coherent signal processing is expected to be enabled by optical frequency combs and with bandwidths of hundreds of terahertz. Data rates. This is time again along the time axis. In data rates, this is the graph that you would see in the technology evolution of the technology of optical fibers, from multi-modes to single modes to coherent to optical amplifiers, WDM, and beyond. This curve was drawn until 2010, but the expectations is that spatial division multiplexing would play a very important role, using multi-mode fibers to carry different channels in addition to the wavelength. Let me just skip this and move on. Long distance has been a challenge, but short distances, as you can see from this, going from communications between cities into communication on a chip. Optics is providing that, and I think this graph shows that there will be more optical presence inside the chip. Space. What is the limit here? The limit here is the wavelength. And the desire is to do localization in 3D. We have Abbe's limit. Can we beat the Abbe's limit? That is the challenge. By how much? That is the challenge. Microscopy and nanoscopy has beaten the Abbe's limit. And in the third dimension, 3D lithography is going to be a very important means of beating and a very important application that would result from the improvement of resolution in 3D. Beating the wavelength limit was done early in the game using post-detection super resolution, using mathematics. You read the image and you try to invert using a mathematical technique. It turned out to be an ill-posed problem, and it didn't lead to great results. But scanning near-field microscopy has beaten the Abbe's limit because it doesn't apply to near-field. And multi-photon fluorescence microscopy has beaten the Abbe's limit. And STED is another technology in the last decade that has also beaten the Abbe's limit by a factor of 20. More is expected. These are examples of using fluorescence markers with technologies that have acronyms like STORM and PALM, and all of these allow us to do 3D imaging at the molecular level with light which has a wavelength in the micrometer range. The Abbe limit will continue to be beaten to death. That's a conclusion. Computational localization is something else, using tomography to beat the Abbe's limit. Precision spectroscopy and metrology along the axial direction, in the z direction. There comes time, because in the z direction, time and space are one and the same thing. So there you could use femtosecond and attosecond optics to do axial imaging, localization by the pulse width. And of course, the metrology people have used standard coherent optics to have lambda over 1,000 at times. And that is by precision optics and axial imaging using frequency swept OCT, optical coherence tomography. That doesn't give us much of an improvement over Abbe's limit, but it nevertheless is a very important technology. And the use of frequency combs for precision metrology would also help us improve the axial resolution by great margins. Then in space, localization in space, you have to shape the beam just like you shape the pulse. You want to shape the beam in space. We hear about vector beams, non-diffracting beams, helical beams, optical vortices, and then airy beams. This is an example of light that bends around the corner and potentially can achieve the task that I highlighted a minute ago. These beams allow you to apply forces on nano objects. We hear about optical molasses, traps, tweezers. Then localization in space means confining light in resonators. The history of optics starts with the mirror resonator, which is a bulk resonator. And it goes on to the ring resonator, and it comes to the fiber ring resonator, integrated optics, and that's all macro or bulk. Then it goes into the micro, and we are now entering the photonic crystal and the plasmonic resonators for localizing light. And materials and structures for spatial localization, as I said, go from bulk into micro into nano and beyond. And these are elements that would use materials like dielectrics, metallic, polymer, semiconductors. Now, the entry of the word metallic, we've heard about that extensively, but who would have predicted that? Metallic optics. Was it there in the vocabulary of optics people in the 50s? Oh, yeah. You go to Born and Wolf and you see a chapter called Metal Optics. And the basis is there. The Drude model is there. But how many decades it took to be able to get the materials sufficiently reduced in structure or enhanced in spatial localization in order to reap the harvest of metallic resonance, plasmonics, and enhancement to the field by these resonances. So metamaterials, we've heard, I don't need to say that. Now the challenge of seeing through objects, I mentioned that. And this graph, which is from my recent book, shows resolution and penetration depth. Now resolution is improving in this direction. And you can see that the many technologies, there is always a trade-off between having a higher resolution and a larger depth of penetration into a material that is opaque or dispersive. And I think that new technologies are going to advance along lines dictated by these trade-offs. space-time that is reading and writing fast. So now, not only I want to localize in space, I want to localize in space and time at the same time. What is happening in this area is you see optical bullets, you see solitons of different kinds, you see space-time cloaking, and the ability to create waveforms that are pulsed simultaneously is going to dictate progress in directions like synthetic aperture imaging, like real-time laser micromachining, like even 3D video display. Display is an old area, and every now and then you get something interesting, but it hasn't really come to change our life in our homes. And maybe I'll skip these slides since you've seen them, but here you could see a combination of the speed and the device dimensions, or the localization in space and the localization in time, and where plasmonics plays an effect. Pass on that. And let me just give this slide, since I think it summarizes what we've heard in the previous talk in a crisp way. Dielectric materials put in layers created photonic crystals. Metal that created plasmonics. Then semiconductors with quantum dots. And then you would have superconductors. That hasn't happened yet. And then you start with 2D and you go to 3D. And then you start with static and dynamic. We've heard about switching. And you start with passive, and then you put gain into these devices. So you have materials, metamaterials with gain. We've also heard about that. And then materials lead to devices, lead to systems. We haven't seen the systems yet. And then quantum structures. We saw examples of quantum structures that lead to quantum devices and quantum systems. That's also futuristic. There's a very good article in OPN that I recommend you read. I'm slowly running out of time. What is the third dimension? The third dimension is amplitude or energy. And what is there? It's precision. Look at the axis here. What are the limits? The limits are a single photon at energy of picojoule. And then this is the National Ignition Facility at energy of megajoule. So we have 14 orders of magnitude of energy. And we can optics can work in this domain and in this domain simultaneously, and there are the advances in each over the next decades. What are some of the advances in the area of very few photons? Single photons on demand. This is a reality. It's not very efficient, but it is a reality, and people do some work with single photons. Not just that, but entangled photon pairs, not quite on demand, but they can be made on demand. And what do these things do? Well, they have fueled the great interest in quantum information, and this is just light. This is linear optics type of quantum information, not including materials where you have buffers and storage for quantum computing. But we see applications like quantum key distribution, quantum communication, quantum teleportation, quantum precise sensing and metrology. Because when you have a photon, you know it is a photon. That is the ultimate precision in a unit of energy. And then quantum computing and more. Along the other directions, we see high-power lasers. High-power lasers have hit the 100 kilowatt in commercial. And solid-state lasers are going to play an important role. You look at this line, it's not Moore's law, but it is maximum power going to 100 10 to the 5, 100 kilowatt of maximum power over a couple of decades. Fiber lasers are also delivering high powers. Would one expect this graph to keep going? I don't think so. I think it would just level. And even ultra fast with high power, that's also progressing, and there would be more along these lines. I'll just skip this slide. In energy conversion efficiency, there's no time to talk about the great things that are happening in photovoltaic solar cells. We've heard some examples of that. LEDs and increasing their efficiencies and the impact it will have on illumination. Smart light is going to be a reality. There will come a time when the normal lights that are flooding this room will disappear. Laser diodes, quantum well, and quantum dots. This is an example of an effort to reduce the threshold current density for diode lasers all the way to thresholdless lasers, although that's controversial. And I'll just come to a summary that optics and photonics is headed toward more localization in time and frequency, localization in space, localization in time and space, 4D and 5D imaging, precise energy control, single and entangled photon sources, and photon number detectors. This is another very important area, detecting these single photons. And greater energy and power, greater energy conversion efficiency. And these advances will drive great expansions in the applications, an enormous menu of applications that we all know. And I will stop at this by a disclaimer and an apology. A fully comprehensive overview of current trends in this old subject of optics and the new subject of photonics is certainly unfeasible by definition. So apology if I ignored your favorable area. I didn't mention the word graphene, for example. Don't be upset. Now, the disclaimer, we all know this famous quote from Niels Bohr. He's my hero, by the way. Prediction is very difficult, especially about the future. But Bohr said also, your theory is crazy, but it is not crazy enough to be true. And I'm afraid what I suggested today ain't crazy enough. Why not? Because all I did is I defined axes of time and space and energy and precision as goals. And I said there are landmarks and challenging points that we want to just drive toward. That's not innovation. That's knowing what the goal is. You march along the goal and you try to meet the challenges. On the way, you discover some disruptive things. But you have to know your goals. And that's what I attempted to do. And I thank you very much.